Okay, well, this lecture was planned to tell you something about my current research interests, but I really want to start spending a few minutes on something that's totally different from it because of its importance. And I could entitle this part of the talk, The Good, the Bad, and the Ugly. Now, the good is a piece of physics which by rights should have led the people involved with it to a Nobel Prize by now, since the canonical 10 years has passed quite a time ago. The ugly is the way this work was attacked by people who had a vested interest in it not being true. And the bad is the consequences of this kind of science, which is that the scientific community not only closed the door on this research, but they locked the door as well, and as a result, very few people know about this. It is actually published in obscure, some of it is published in obscure journals, perhaps I shouldn't say obscure in Germany, Naturwissenschaften and fusion technology and so on, but most people don't know about this. So I'd just like to take a few minutes going through to tell you something about this. The discovery, of course, if you haven't worked this out by now, was the claim by Fleischmann and Pons in 1989 that they could get fusion to occur under fairly ordinary conditions rather than extraordinary conditions. What happened after that was that various people tried the experiments. Some succeeded and some failed. Some of those who failed worked deliberately to discredit this. They said, we didn't see it, we think this is incompetent experimenting, and that somehow was the end as far as the scientific community at large was concerned. But meanwhile, people tried, and a lot of people got this rather difficult experiment to work. They got fusion to occur under a variety of conditions, and there's a website, lenr.org, which has a library giving hundreds of papers on this. So what I want to do, I don't want to take too much of my time on this, but just talk about one that I am particularly interested in because, well, the way to find out if something is valid or not, the best way is to visit the lab and see what's going on and talk to people. I visit two labs, and last year I visited the laboratory of Thomas Claytor. The work was originally done at Los Alamos when it was funded by the NSF. Now it's privately funded and is done a short distance away. Here's one of our papers, which I think was published in Fusion Technology, tritium production from deuterium discharge, and the abstract begins, over the past year we've been able to demonstrate that a plasma loading method produces an exciting and unexpected amount of tritium from small palladium wires. Here's one of the graphs in that paper. You see the control samples at the bottom with very little happening. The upper graphs show tritium, tritium is radioactive, which makes it a good thing to look for. You can identify what is decaying by using a scintillation counter, and also if you keep it a long time, you see it decaying over time at precisely the right rate. This is one of the papers you can see at lenr.org. LENR stands for Low Energy Nuclear Reactions. As I say, I visited the lab. This is me, and the person on my right is Tom Claytor, whose experiment it is. I think he first discovered it in 1990 and has been, as a sideline, continuing since. And when I went there, he was looking at various metals to see which ones gave the highest yield, which would obviously be important for practical applications. We may soon see practical applications. I know of one British firm which hopes to have something producing water heating maybe in a couple of years. This shows the glow discharge. This is my own photograph, and this is the apparatus which is apparently generating tritium. They're pretty careful people and have looked for alternative explanations for why they might be seeing tritium, and nobody's discredited this experiment. Neither has anybody discredited the calorimetric measurements in the Fleischmann experiment, though they made an error when they said neutrons were produced. So this does seem to be a genuine thing. Hopefully our attitudes will change. Let me just say about the propaganda aspect. This is one typical propagandist book by John Huizenga. The propagandists are mainly people who work in high-energy physics and don't know anything very much about condensed matter, where things may be very different. Here's the reviews, authoritative, frank, hard-hitting accounts of the cold fusion fiasco, etc., of Seaborg. Now, it's interesting that Seaborg gave a lecture where he joked about how he managed to get cold fusion abolished. He was asked to advise President Bush.
I was called to Washington to brief President Bush on it. It was a real dilemma. What should I do? I decided, well, I'm going to take my background as a nuclear scientist and really come to the sensible conclusion that this work was not right. I said, you can't just go out and say this is not valid. You're going to have to create a high-level panel that'll study it for 6 months, and then they'll come out and tell you it's not valid, and that's what he did.
Now, the people in charge of the panel were Huizenga, who we've seen, and Norman Ramsey, who is very suspicious as to the arguments that this wasn't occurring, and he actually refused to sign the summary report. And he and maybe some other people here are of the impression that this is probably a genuine effect. Now, it may be that we'll soon see a return in intelligent debate. Someone who's a reporter for Physics World, the British equivalent of the British equivalent of Physics Today, he covered an experiment which was supposed to demonstrate fusion by a different method, and he wrote a blog which has had some fairly intelligent debate, and he actually is interested in finding out more and may perhaps attend the next conference, and perhaps Physics World will be the entry point for this, and normal scientific discourse will then take place. Okay, well, so much for cold fusion. I now want to get on to what I'm interested in myself, which way for physics. Now, there are, I want to contrast two views as to the fundamental basis for physics. Now, what's usually happened since the time of Newton, at least, is you have a universal formula and everything comes out as a solution of that formula. It's a fixed formula from which everything is derived. Now, there's an alternative that self-organization plays an important role, and the laws you observe come about from self-organization. What is self-organization? Well, it means organization from within, not from outside, and one example is a crystal lattice, that nothing says directly you should form a lattice. What happens is, as the molecules go together, they self-organize, and a lattice comes out. Now, I'm going to discuss how this might happen at the fundamental level of reality. Now, some historical precedents. Some of you may have heard John Archibald Wheeler's thoughts on this subject. He wrote an article called Law Without Law, where he suggested there aren't really any fixed laws of physics, and the laws emerge by some feedback process, that observers observe what's happening, they in some way participate and change the laws. This idea has come about in many contexts. Stuart Kauffman has applied this self-organization idea in biology. He claims that self-organization is important as for things happening in biology. Stephen Rosen, has some rather deep books. They're based largely on Martin Heidegger's phenomenology and Merleau-Ponty's phenomenology, which is essentially saying you should talk about phenomena. And also one of his ideas is that science is about the search for order within something that is largely disordered. Alexa Yardley is a non-scientist with whom I've been collaborating by email recently, and she has some rather interesting ideas on how self-organization actually works, and these are found in part of well, these have helped to shape what I'm talking about later. The last one, well, a comment by songwriter Samantha Parton just happened to move me in the direction of thinking critical phenomena were important. Okay, well, let me now move to basics, the sort of a good point in which this discussion should start. I have here two questions. Where does biology begin? And what are the special features of systems near a critical point? Now these, as we'll see in a moment, are connected. Now, of course, if you're going to ask where does biology begin, you can't really answer that without having defined biology. So it's a rather tricky question, and you have to feel your way to what the answer might be. So, as I said, I got the idea that critical phenomena, or something related called the edge of chaos, which is one of the things Kaufman uses in his idea, in his writings. So let's get into critical points and see where biology might fit in there. Well, the key point about, well, one of the things about critical points, these are points where you get a phase transition, continuous phase transition, and as you go to that critical point, you get fluctuations which are very large. They're sort of not like ordinary thermal fluctuations, which slowly rise with temperature. They get very large and in principle infinite as you go through the critical point. Something I should have put on this slide is that nonlinearity is important, which isn't the case very much for normal fluctuations. This is because of a high amplitude. Also, they may persist in time. They're large in amplitude, spatial range. You get large oscillations of large wavelength. Also, you may get persistence over time. Now, when we talk about persistence, that starts off as something relevant to life, because the feature of, when you think of natural selection, life is what persists. Special configurations that will persist over time, but obviously that doesn't really get us far. There's a question of life. So one more point in the whole picture connecting critical fluctuations in life is the hierarchical aspect. Well, actually fractal. Fractal means that the same things happen at all length scales, which happens to a certain approximation in critical points, as Ken Wilson used in his Nobel Prize-winning work. Biological systems have hierarchies of structure, also computer programs. However, that connection doesn't work out very well, because the structures are entirely different at different levels in biological systems. Okay, well now, what is the biological extra? Well, I'm gradually working towards this thing. Special structures and also interrelationships. Now, interrelationships between structures is what will prove crucial. Now, let me just say at this point, what I'm talking about is entirely qualitative and intuitive, so it's in no sense proved, but it's the kind of thing, it's not philosophy, because one should be able to produce computational models and see if things really happen as the qualitative theory suggests. Okay, now one curious thing about this kind of structure is that it's not very well defined. This is partly because of the critical fluctuations. The kind of ill-defined structure when as at a critical point is a bit like the structure of fog. If you ask of a fog patch, where is it, what is its shape? Well, that's not very clearly defined. You can sort of make arbitrary definitions of what a fog patch is, but it's a little blurred. Nevertheless, we can still talk about fog patches. We can say a fog patch is moving. So this is a thing that happens in this rather strange world. In fact, the whole methodology would need to be changed in talking about critical points, because you can't use very precise descriptions. Descriptions are very subjective, which in fact winds into the whole theory. Nevertheless, you can use models which enable you to understand. This is somehow what language does. It enables you to discuss things even though it's hard to say what the definitions are. Right, well now I'm really going to get into how biology emerges. I have 4 things here: structure, memory, individuality, and relationships. Now, the line below those with P, and P means physics and B means biological, which really means which realm of discourse these things happen in. Well, structure is pretty well a physical thing. Of course, you get structures in biology. Memory is something that endurance of structure over time is in both. But now we come to things which are more like biology: individuality and relationships. What do I mean by individuality? Individuality could be defined as saying every instance of a phenomena is different in important ways. Now, the important ways is a key thing, because if you're dealing with a disordered structure, then every instance of a disordered structure is different. The particles have a different arrangement, but the differences are not very important. But in the biological realm, differences in structure are important. Mutation will change the way things behave. So we're now starting to move into the biological realm, the realm of biological discourse. And then relationships are important in biology. Systems talk to each other and things happen. They work together because of the way they interrelate. So this again has a biological flavor, especially the way things cooperate. Now, to say a little bit more about structure, one kind of structure you can get is a static structure. For example, an array of spins up and spins down in some particular arrangement. Well, that isn't too interesting in this context, but you can also get dynamic structures. For example, resonant systems may have frequencies that connect. In the solar system, there's some groups of free objects whose frequencies are in a linear relationship. So that's a kind of dynamic structure. It persists over time and is peculiar to that system. Particular triplets have particular relationships between their frequencies. So that's a thing which is probably more interesting and would be used in models. Now, individuality is important in biology in the sense that individual molecules have their own special properties. But now we're not talking about chemistry, we're talking about some pattern of fluctuations and the way these could self-organize by, for example, relationships between frequencies. Now, another thing which seems to be important, and I think may be the key to how functionality, intelligence develop, is that these fluctuations I talk about, which might be, say, like the thing you have at a laser which is just switching on, there'll be a certain kind of fluctuation. But fluctuations at a critical point may keep changing. In particular, 2 fluctuations may merge together into a bigger one, or one fluctuation may split up into 2. It all depends on, well, for example, fluctuations may merge when the frequencies become close together. How can you treat this mathematically? Well, there are two ways of talking about them. One is more topological and the other more quantitative. You can talk about a cycle, for example, which is one of the things in Kaufman's theory. A system may go through a cycle, and once it's in the cycle, that cycle may tend to persist because you get back to the starting point. You may talk about movement, change over time. The thing which is particularly important is the idea of an attractor, a system which might go over the whole of a phase space, may, through its dynamics, be limited to a particular region, which will mean you get important correlations between parts. You might be able to model this more quantitatively, as indeed has been done in some models of chaotic systems. Okay, now the discussions with my collaborator have been, well, first of all, I've already said about cycles being related to movement. So you might find, for example, that one thing going through a cycle is coupled to a movement elsewhere and vice versa. This is the kind of thing which one has in biology. What's more interesting is relationships. Now, the interesting thing is that you can get various levels of a relationship which will be associated with what I talked about before, two systems merging. Now, if they're partly merged, then they'll become correlated to a degree and yet have freedom. And there may be this kind of thing can be modeled in terms of attractors. Two systems, when they're uncorrelated, will have points which will move all around phase space. When they're merged into one, this will mean they're in a small region of phase space, attractor region, whereas partial merging is somewhere in between. You may get a situation, which Kaufman has discussed, where the system is sort of frozen in one region, but then some external activation moves it into a larger region, then the activation level becomes less, and they will freeze into a lower region, and some regions which will be more stable than another. So that's a general mechanism which may produce more stable situations and lead to evolution. These relationships you can expect to evolve through systems doing things together. As they do things, there may be more noise, as it were, or less noise. Okay? And the system may then find the most stable situation, and these we hope may correspond to a gradual growth of functionality. And there'll be a progression. Systems may interact. They may be able to coexist, which means that there won't be so much noise around to cause them to disintegrate. And then they may be able to make the noise less, and this will be a cooperative regime. There are certain tasks which are important in the biological context. For example, feeding, and you might get feeding on maybe some equivalent to feeding, with feeding on fluctuations of the right kind, which may sort of keep systems going together better. Reproduction, the system may be able to do something which produces a similar system. The systems and relationships that accompany them well will tend to survive, so we'll get a kind of natural selection. And now what we hope would happen when you went through models in detail is that forming relationships goes on, getting more and more complex structures. For example, a system might function as a code, so any kind of functionality may contribute to stability. So you may get particular kinds of relationships emerging just through these processes occurring at a critical point. So some systems will act as codes directing the movement of other systems. Maybe structures emerge, so you get quasi-software. Also, systems may be able to work together to make a kind of objective reality which persists more again. Okay, now you can argue that there are at least some potential links between this theory and conventional quantum mechanics. For example, there may be, if you've got some systems which are used in creating an objective reality, these systems really correspond to potentials, because whether a particular thing which you have codes for is realized may depend on the circumstances. So, in fact, potentiality, it is Heisenberg's statement as to what's important in quantum mechanics, is potential is expected in this kind of situation, as these processes deal with and represent possibilities. Okay, symmetries may come out naturally, because symmetry present in one of these local systems might, as the system accumulates, produce a greater degree of extended symmetry. But on the other hand, one set of systems may be working to create symmetry, while other systems may like to break that symmetry. So this can account for both symmetry and symmetry breaking. So the question is, let's see, do I have a slide for this? yeah, I want to say, which isn't in the slide. What has happened in fundamental physics so far is people have encountered a problem of fitting together gravity and standard model. They found one way in which these might fit, but there's no experimental evidence. And who's to say if this is the right way? There may be many ways of doing it. In this approach, you'd say, well, there isn't any law. The law you have actually emerges, and it may have some symmetry. This may be a way of creating a world, as it were. So we have to see what was really needed is to develop these ideas by trying out models. This will not be a simple task. It's difficult enough modeling physical systems, biological systems. Will involve more modeling, but it's something that should be possible, and so we would try and characterize all these steps, create models, and this is, I think, a more practical project than string theory, because in string theory you can just do the mathematics and not relate it to real things unless we happen to find all the right particles. Well, this may seem a strange set of ideas. I thought Jane Austen's Pride and Prejudice would be a good point in which to conclude prejudices against these kind of ideas. You can even get the Physics Preprint Archive, which is run by string theorists, to bar all papers that might challenge string theory, or at least banish them to general physics. But tomorrow's crazy idea sometimes becomes tomorrow's profound insight. So we'll have to see what tomorrow brings. Thank you.